Hello and welcome. Today we're going to solve an interesting integral with an elegant and a strange solution. This is the Gaussian integral, evaluated from negative infinity to positive infinity. This integral is, actually this function is a normal distribution function, and it's so popular in probability and statistics, and its graph looks something like this. There's a bump here, it's a bell curve. So we're going to evaluate this whole area from negative infinity to positive infinity. And to do this, we're not going to use a usual integration trick like U substitution, trig substitution, integration by parts, partial fraction decomposition. We're not going to use any of them. We're going to use a strange method using polar coordinates. To start, first we're going to call the integral I, and we're going to square it. So we're going to say this is equal to, no, actually no. I squared is equal to our integral squared. And to square the integral, we're going to multiply it by itself, and by multiplying it by itself, we're going to change the variable from x to y. So we're multiplying an integral of x and an integral of y. So I squared is equal to our first integral e to the minus x squared dx times an integral, actually the same integral but just with a different variable, e to the minus y squared dy. And to do this multiplication, we're just going to multiply the two functions and write it to the double integral. So this expression here is the double integral. And I can just combine the exponents, x squared and y squared, and I can say minus in the front and x squared plus y squared dy dx. And why did I do this? Now it's even more complicated. It's a double integral. It is a three-dimensional variable, three-dimensional graph, and I have to find the volume of this function. It's like a three-dimensional bump. To do this, I'm going to transform this function from the Cartesian coordinates to polar coordinates. And to do that, I'm going to multiply the function something called Jacobian matrix. And the reason I'm doing that because when changing a function for a Cartesian function to a polar function, the function stretches, and to take care of that stretch, we need to multiply it by something called Jacobian matrix. In polar coordinates, x turns into r cosine theta, and y turns into r sine theta. Polar coordinates is just our Cartesian coordinates, but to represent any coordinate, we use theta and r. For example, to represent this point, we say this point's distance with the origin and this angle, theta. We use r theta instead of xy. And in polar functions, x coordinate is r cosine theta, because of if you project this in the point onto the x-axis, this here is r cosine theta, and if you project it onto the y-axis, it is r sine theta. So now we know why x is cosine, r cosine theta, and r sine theta. Y is r sine theta. And here's the Jacobian matrix. It's del x over del r, and del y over del r, del x over del theta, and lastly del y over del theta. We're going to compute the determinant of this matrix and then multiply it with dy dx. No, we're going to multiply it with dr d theta and change dy dx to that result. If we multiply del x over del r by del y over del theta, so basically a determinant of a matrix is this times this minus this times this. So del x over del r, so r cosine theta's derivative with respect to r is just cosine theta. Multiplied by this function's derivative with respect to theta. And if we differentiate it with respect to theta, then it's just minus r cosine theta. So there's a minus r. Actually, no, there's no minus. Sine theta's derivative is just cosine. Minus this times this. So what's this? This is r cosine theta's derivative with respect to theta. It's just minus r sine theta multiplied by y's, so r sine theta's derivative with respect to r, which is just sine theta. So this is r cosine squared, r cosine squared theta, and these minus make plus, and it's r sine plus r sine squared theta. If you factor out the r, we can see that cosine squared plus sine squared, which is just 1, and we can say that this is just equal to r. So, now we know what to change our differentials with, which is r dr d theta. So now dy dx equals r dr d theta. If we rewrite the function, this is just it's just r, x squared plus y squared is r squared here, and this inner integral will be, let me just write it, e to the minus r squared times r dr d theta. This inner integral right here is an integral of r, and r is the radius of a circle, and it can at least be 0 and at most be infinity. And the outer integral is an integral of theta, and theta can be 0 to 2 pi. This is an angle can be at most 2 pi. So let's look at the inner integral. It's from 0 to infinity, e to the minus r squared r dr. Let's write it over here. So the inner integral is e to the minus r squared r dr. We can use u substitution to solve this. We can say that u is equal to r squared, and then du is going to be equal to 2r. So it's e to the minus u squared, sorry, it's e to the minus u times 2r, and we have 1r. To have 2r inside, so we have r and we need 2r, so we're going to multiply this by 1 over 2 outside of the integral, and say that this is just du. So it's just e to the minus u du from 0 to negative infinity. At 0, it's so we can write it as e to the minus u from the chain rule. The negative sign comes in front of e. This function evaluated at 0 and infinity. At infinity, our function approaches to 0 because it's e to the minus infinity and it's 0. At 0, our integral is just 1, but minus 1. Sorry, here's a minus sign, and it's because it's 0 is the lower bound, we need to subtract it from the upper bound. Upper bound is just 0. 0 minus 1 over 2. So it's plus. So our inner integral is just equal to 1 over 2. So we have evaluated the inner integral, and we can rewrite our expression as 2 pi and from 0 to 2 pi of 1 over 2 d theta. And this is equal to theta over 2 evaluated at 0 and 2 pi. So our lower bound is just 0, and our upper bound is 2 pi over 2. 2's cancel out, and we find that our integral is equal to pi. But remember, this integral is I squared, and I was our initial integral. So we can say that I squared is equal to pi. And because it's squared, we can just take the square root of both sides and say that I, which was our initial integral, the e to the minus a squared, is equal to square root of pi.